is Andy Schweitzer, and welcome to a short video on an introduction to equilibrium involving a whole gamut of different types of chemical reactions, some involving gases, some involving aqueous compounds. And I'm going to just do a quick review of introKcKp. We'll also be looking at a few other things. One is going to be how are Kc and Kp different? How do I convert from Kc to Kp? And what happens when you manipulate equations? What happens? How does that affect your K value? And then lastly, we'll do actually those manipulating reactions and how it affects K. That's what we just did right here as well. Actually, there we go. Those are two topics there. And then we'll do some two advanced problems. So those are our main concepts which we will cover here. And introduction to introKcKp. Now keep in mind, as we are doing a chemical reaction, we have, let's just say A goes to B, and let's just say hypothetically that these are both aqueous compounds, or let's just say they're gases for that matter. So we'll track the gas pressures of these two as we move along. If we have a reaction, and I would just use this little gauge that I often write down, and it looks like a little car gauge or gas gauge, and of course in the end we will reach equilibrium, which is going to be, let's just say, on right here. Okay, this would be a product favored reaction, but you know, we dump a whole bunch of A into a container, and all right, A is floating around this container, and give it time, it will eventually form some B, and then B will back form some A, and eventually will turn out to an equilibrium over here, where the concentration of the products are higher than they are of the reactants. This is a product favored reaction. But currently right here, since all we have is A, we are currently like basically right here, okay? We don't have concentrations representing this value here, so we call this Q, reaction quotient. And eventually it will proceed over this way. Now if we were to graph this thing, it would look like so. We'd have time on the bottom axis, and this would be concentrations on the x-axis. I'm not going to put that on there, but on the bottom we might have the concentration of P would be right here. P's concentration would be here. There's none. And then we would have concentration of R, I'm going to say is right here. And I will track the concentration of P with the black marker, and I'll change color for the other one. But let's just say at this point it would just continue like this, increasing, 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 and then all of a sudden it would just level off. The reactant would be decreasing, 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 and eventually it would just level off. These should be, my marker's a little off, but these should essentially be at the same spot where they would essentially change. They would stop moving. My lines are a little off, but either way, at this point, this is right here is where equilibrium has been struck, okay? And this is where K is now established. I would be moving that way, gaining concentration of product, losing concentration of reactant, and I would form a balance K at this point. How long that took? It just depends on the reaction. Depends on the catalyst available. So how we track these concentrations will determine whether we use Kc or Kp. Now Kc is any chemical reaction in which the concentrations are being tracked in moles per liter. For Kp, okay, if we're using pressures, okay, this would be anytime we're tracking these concentrations using pressures of gases, so it has to be a gas, and this will be in atmospheres. And we will be only be using or tracking the individual partial pressures of each individual gas. A little brief explanation of that would be, okay, let's say we have this same reaction, and when it comes to equilibrium, we have some A's in here, right, as the equilibrium is stating, but we also have a bunch of B's, and we should have a few more B's than we do have A's, because this is a product favored reaction. Okay, Now, this container reaction is at a specific temperature, and this K, of course, right here is temperature specific. If I change the temperature, I change my ratios of products to reactants. That K is locked for a certain temperature. Let's just say this is a gaseous, so I don't know why I drew that line there, but let's erase that line. I don't want to make it look like I have an actual level in there, but there we go. We'll take that out, and I will simply seal it up, and I have all these gases sliding around inside here. The container is rigid, so it has a certain volume. And okay, so of gases, we use PV equals nRT in order to measure these gases. The temperature is constant as far as both gases. R is 0.0821. That's also constant. The volume is constant. Okay, so these two items here are both constant. So therefore, the pressure and the number of moles are directly related. More particles, more pressure. The pressure and the number of moles are directly proportional. We call this partial pressure. Of the number of particles you have, how much of the pressure is due to those particles. And if you put in just the A particles in here, you'll get the pressure of just A. So the only way to change the partial pressure in this particular container of B would be simply to add more B. I could add some other chemical here, isn't going to change the partial pressure of B at all. As long as the volume is constant, my pressure of individual pressure of B is solely linked to the number of B's. Same thing for A. So we're tracking the individual pressure of that individual substance. Now, otherwise, let's see what else we have here. Let's move on to our next page. How are Kc and Kp different? Well, essentially, I've already covered that. Kc is involving moles per liter. This is involving atmospheres. And that is somewhat different in how we're tracking our concentrations. The next question would say, okay, how do I convert from Kc to Kp? And I'm actually going to do this slide first, writing expressions for Kc and Kp. And that is one difference between Kc and Kp is how you write your expressions. Kc is only going to include things that are in moles per liter, whereas Kp is going to use things that are in atmospheres. Now, gases can be measured in moles per liter, or they can be measured in atmospheres, either one. But aqueous compounds can only be measured in moles per liter. They cannot be measured in atmospheres. So if I want to write this expression, K is a ratio of concentrations of products over concentration of reactants. Okay, now, careful here. I want to do Kc, okay, Kc. So D is a gas, so the concentration of D, all right, and bracket, clearly listed bracket. I would put, if there's a 2 here, I would put a 2 right here. Concentration of this guy would be C. Okay, 1 right there, so I would leave a 1. Solids cannot be measured, so solid would be out. This is a gas, so I would go concentration of A to the first, because there's a 1 right here. If I'm doing Kp, however, it's going to be slightly different. I'll have the D concentration, I should say now, Kp is pressures. You cannot use these brackets because that's involving a moles per liter. Even though I think it kind of measures the same thing, we must list it as a P for a pressure of gas D, all right? And I'll put it in parentheses. Advanced Placement Exam requires parentheses here, and I will square it. And this guy is not going to be included. It's aqueous. It doesn't have a pressure, so it's not going to change. This is the solids out, and in the bottom will be the pressure of gas A, and it'll be 2 at the first. You can put a parenthesis if you want, but it'll be 1. Make sure they're clearly parentheses and not brackets. Okay. Now let's go back to switching between Kp and Kc. This is an equation that used to be on the laminated sheet for advanced placement exam, and as of 2013, it just isn't there. So I'm assuming this is really just a plug and chug formula, one that maybe they're not expecting you to do anymore, or they would give it to you if they need it. Just literally plug numbers in and plug numbers out. So, but I'll walk through it quickly. If I have an equation that I'm measuring in Kc, and I want to know what the correlating Kp, so if I calculate out this value, how can I get this one? Okay, it doesn't have a lot of practical uses. It's literally just converting from one form of measurement to another. Now, in this case, what I do is I say, okay, well, if I give a Kp right here, I just simply plug it in, Kp, and R is going to be 0.0821. Put your temperature in there, so let's just say it's standard at 273, and then N. Okay, it says change in N, and that would be the old laminated sheet even told you it was the sum of the product gases, so it must be gases, minus the sum of the reactant gases. Here's an example. If I have A gas plus B gas yields C solid. Okay. Let's go one more plus D gas. All right. This case, I have a total of 1 and 1. I have 2 product gases. Got to do the product first, so there's only 1. Let's scratch that. 1 product gas minus the reactant gases, which is 2. This would be minus 1. That gets plugged in right here. And you take this value, which is the value of Kp, multiply to the, well, these two guys are in parentheses, so technically you'd multiply those first, and then you bring it to a power of -1, multiply pi times Kp to get Kc. Okay? Pretty simple plug and chug formula. All I would say is that there is one little shortcut that I would be aware of, even though this is not on your laminated sheet anymore. The shortcut I definitely would be aware of. It used to show up in a lot of multiple choice questions. With a new exam coming up, I don't know how much is going to show up, but here's how it works. If we have A gas going to B gas, in this case you use your math, and let's say let's say Kp equals X. Okay, I want to find out what Kc is. All right, so what I do is I take my formula that's right here, and I would say, okay, well, Kp equals X, so Kc equals X times 0.0821 times, let's just say it's 273, and I really need to put my power here. It's product gases minus reactant gases. That would be 1 minus 1, which is 0. And of course, if anything to the 0 power means this whole little thing is 1. Therefore, Kc actually equals Kp. So the shortcut here is that if your gases are equal to each other, then Kc equals Kp. I could even have a C solid here. That wouldn't make a difference. Kp still equals Kc. Important thing here, I've seen multiple choice questions on advanced placement exams where they'll have which of the following equations is Kp equal Kc, and they'll have a whole list of equations, and you just need to go through each one of them and see which one has where the units, the coefficients are equal. Okay, we already covered that. All right, manipulating reactions and how it affects K. All right, so Kc or Kp, it just doesn't matter. If I have A plus B yields 2C, all right, and let's just say K equals X, all right? And first way I can manipulate the equation is to reverse it. Okay, technically this reaction goes both ways. If I reverse the reaction, 2C A plus B, how will that affect my K? Technically the same reaction, but it's just written, the other way. For this reaction, K is equal to the concentration of C squared over the concentration of A, concentration of B, and we're done. So whenever we write this one, K is equal to the concentration of A, concentration of B, over the concentration of C squared. So they are flip-flopped. Therefore, your K is equal to 1 over X. So anytime you reverse your reaction, you reciprocal the K value. Okay. Now, what if we were to multiply or divide the coefficients? Okay. Now, here's the deal. I can take this reaction, let's say the first one, I can go 2A plus 2B yields 4C. In this case, we have a situation where we take our K value is equal to the concentration of C to the 4th power, concentration of A to the 2nd power, and concentration of B to the 2nd power. In this case, whatever this is going to actually be K will equal X squared. So whatever I do to these guys, in this case I took all my equations and I multiplied times 2. This became 2, 2, and 4. Whatever I do to this thing ends up affecting the power of that guy right there. If I were to multiply all these guys times 3, then this would be raised, K would be X to the 3rd. All right? I could even take all my coefficients and cut them in half. So it'd be 1/2 A plus 1/2 B equals 1C. This would be equal to K equaling X to the 1/2. Or another way of saying that is the square root of X. All right? I think that is, let's see, anything else? Oh yes, we have a couple problems and we'll run through here. With these problems, we would want to be able to do two main things. I'm just going to write this equation out. We have an equation N2 plus 3H2 yields 2NH3. For the expression here, I have K equals the concentration of NH3 squared, concentration of N2, concentration of H2, and cubed. So we also have our ICE table, and SE is how I would usually say it. Initial concentrations, stoichiometric ratio shift, and ending or equilibrium concentration. So in these problems, we have conditions that can be given either initially or equilibrium conditions. Keep in mind these equilibrium conditions can be instantly just pushed right into the equation. The initial ones, those are initial conditions, so they cannot go into the equation. But our overall objective is usually to find 99 times 100, either to find equilibrium, some sort of missing equilibrium concentration, or to find a K value. The K value is, of course, a nice tool that could be used to find other equilibrium concentrations. Okay, but let's look at this problem. Again, set your equation up, plug in the information they give you, and then look for your pathway to the problem's answer. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to maintain equilibrium of 472. Only reason why this value is here is because K is temperature sensitive. Therefore, they'll usually give a temperature just to show you that we're holding at a temperature. An equilibrium mixture of gases, so notice that it says an equilibrium mixture. That means they're giving you the ending concentrations. Was analyzed and found to contain 0.1207 moles per liter of the H2, N2, and NH3. From these, calculate the constant Kc. So because they're giving me the actual concentrations, and I'd be cautious that they're not giving me the answer in moles, they could give you this in moles and give you a volume in liters, and you would need to divide that to get molarity, but I always plug molarity in these problems. Never going to put moles in. So the H2 is going to be 0.1207, and then the N2, which is this guy, is 0.0402, and for the last one we have 0.00272. A few things I might note here is that they're giving you 4 sig figs here, 3 and 3. So I would try to hold 3 sig figs almost always on an advanced placement exam. Got these values, you simply plug them in here. The K value equals 0.00272, and I would take this thing and I would square it. I would take this guy and put 0.0402. That's the N2, it's left alone to the first power, and this is going to be 0.1207, and this guy would be, looks like it's getting cubed. Okay, plug them in your calculator and you get a K value. I'm not going to punch in a calculator because I think that is something you can do on your own. At this point, let's go to the next problem. Okay, the other process, same chemical reaction. Okay, they're giving me a K now. It's a different temperature, so different K, and they're doing Kp in this case. A couple things to notice. Again, we have all gases, and I don't have that labeled a gas, but it is a gas. In equal mixture of 3 gases, the partial pressure of H2 is this one's that one, N2 is that. What is the partial pressure of NH3? Okay, write the equation out. N2 plus 3H2 yields 2NH3. My K is going to include all of them, so they're all gases, is equaling to the concentration of the NH3 squared, concentration of the N2, I should say the partial pressures, not the concentrations, but I sometimes think of them as being the same thing, but they are not. Well, they're close. Cubed, and this is squared. Okay, initial stoic ratio, equilibrium. All right, so they're giving me all of these equilibrium partial pressures. H2 is 0.928, N2 is 0.432, NH3 is, well, it's unknown, and that's actually what they're asking for. So again, I can plug these values in here. They also give me K, so I'm going to just start plugging values in. K is 1.45 e to the -5th equals this guy. I'm going to just pose as being x because that's the question that we want, squared, and then this would be 0.432, and this guy here is going to be 0.928 cubed. At this point, you would cube it, multiply, kick it over, multiply, square root both sides, and you would get the x value. It is anticipated that you can solve that problem as well. This is just a start of the introduction to Kc and Kp. Thank you very much.